So recall the linear Schrodinger equation in the video of applications. DTU, I delta U, inflation, U x naught x0, U naught x, okay, x in R and T in R, okay. So, in that video we saw that we defined the solution by making Fourier transform. This that we haven't, it was this that we haven't defined it, but as the equality when we resolve the differential equation for it over 4 pi it, okay, it and this to the n over 2 convolution u naught, and it was equal to e to the minus 4 pi, well, squared, it psi squared, and here is multiplied by u naught transform. Here is an anti-transform. Okay, so this a similar thing we did on the applications video. Okay, and now we are going to use that this function e to the minus pi absolute value of x squared transform is equal to e to the minus p psi squared, and that e to the minus x squared over 40 transform, but this over 4 pi t to the n over 2 psi transform is e to the minus 4 pi squared t absolute value of psi squared. Okay, so now let's consider the Gaussian function e to the minus pi absolute value of x squared as our u naught. So we saw u xt is going to be e to the minus 4 pi squared it psi squared multiplied by u naught transform psi, all anti-transform as we saw, but now we know what u naught is, and we have to transform, and so we will have this is equal to e to the minus 1 plus 4 pi it pi psi absolute square, let's say, and all this has to be anti-transform. Okay, so anti-transforming that is going to give us 1 over 4 pi it n over 2 multiplied by the exponential e to the minus pi absolute value of x squared over 1 plus 4 pi it. Okay, and let's separate this into exponentials. Okay, so this is 1 plus 4 pi it n over 2 x or minus pi to the value x squared over 1 plus, well, 16 pi squared t squared, and another exponent, well, 4 pi squared it absolute value squared over this again, 1 plus 16 pi squared t squared. Okay, so this is the solution when we start in this function, in this Gaussian function. Then we have this function that it says how is going to be the evolution. So notice that when t is much greater than 1 and absolute value of x is less than t, then the solution is going to be bounded below by a constant multiplied by t to the minus n over 2, because as we can see here, this exponent has a negative, uh, this e to the negative exponent if t is greater, much greater than 1, and this especially, t is greater than x, this will go to 0, this will go to 1 all, and then we will have this t, basically being here, this t to the minus 2, and n of 2 as a bound for the solution. Okay, so as we said, in this case, this will be a constant, no, because e to 0, okay, and if absolute value of x is greater than t, then the solution decays exponentially. You can see that again here, and you will have a mix now if absolute value of x is greater than t1 half, where you will have now the exponential with an I important, and then it will oscillate. Okay, and we can say that the absolute value of the solution will be bounded between a constant c to tn minus n over 2 divided by the characteristic function. Okay, absolute value of x um, less than t. Okay, um, of x, and well, this less than equal, as we said, another constant. Let's say this is cp, let's say c small, divided by t minus n over 2. Okay, so now let's write the solution in terms of convolution, so make the anti-transform of this, the product of the convolution of each anti-transform. So we will have that this is equal to integral in Rn of ei absolute value of x minus y squared of 40 all this over 4 pi it n over 2 u naught y dy. Okay, so if we make this absolute value, we make this it squared, we will have then this integral dependent of dy, so we will take out the part that has the x, e to the I x squared over 4t. Let's take out the constant 4 pi it n over 2, and now we will have the integral Rn of e minus 2ixy over 4t e to the I y squared over 4t multiplied by u naught y dy. Okay, so you can see that this can be a Fourier transform, just taking into account this as f, and we will have to make have to change variables to obtain the formula, and so this will be equal to, okay, we have this x squared over 4t over 2 pi it n over 2. Now we will have this function is going to be the one transformed, this is an I, okay, squared over 4t, okay, here's the absolute value and the variable, u naught, this is going to be transformed, and now as we make a change in variables, here we will have x 4 pi t. Okay, so now if we call ct equal to 4 pi t to the n over 2, then we will have that ct multiplied by e to the minus I x squared over 4t multiplied by uxt will be equal to this e to the I after the value of y squared 4t u naught for x over 4 pi t. Okay, because this that we got here was equal to u xt, the solution. Okay, so this is a property of the solution of linear Schrodinger equation. Okay, so if u is a solution of the linear Schrodinger equation, then we have the following properties. Or let's say, what other things are going to be solution? Well, first of all, you will have that e to the I theta uxt, okay, with theta fixed, okay. Then we can say that u of x minus x naught and t minus t naught, okay, and x naught is in the real, okay, rn t0, okay, is r fixed, okay, so this is also going to be a solution. Then axt, where a is any orthogonal matrix, uh, n squared, okay, matrix. Then okay, so I know u of x minus 2x naught multiplied by t, okay, multiplied by e I x minus x naught minus x naught absolute value squared t, okay, and x naught fixed, okay, and another u5 fxt is well, this is the famous rescale, and lambda naught 2 multiplied by u of lambda x lambda squared t lambda real fixed, okay. Okay, and finally solutions of this type: 1 over alpha plus omega t and over 2 multiplied by the exponent of I omega multiplied by natural value of x squared over 4 alpha plus omega t multiplied by u of, well, gamma plus theta t alpha plus omega t and x alpha plus omega t. We seen this before, something like this. And in this case we will have here these factors alpha theta minus omega gamma equal to 1 condition. Okay, this will also satisfy the linear Schrodinger equation.